Going on, class? Welcome to another lecture. Dr. Nee here, and we are about to go into a new chapter. We've been talking about chapter 12, but we're going to double back and look at chapter 9, which deals with stress transformation. Stress transformation. So let me go ahead and pull up really quick for you this image here on the screen. In your book, you would see this picture of some turbine blades, right? Some turbine blades, not wind turbines, but turbine blades, which are subject to very complex patterns of stress. These things are at angles. You got wind, you got the mechanical stresses that's been applied. You have so many different things that these things are experiencing. And when these stresses are occurring, they happen at various types of angles from every which way in different directions. And so when we think about it from a 3D state, what we are able to then simplify and understand as engineers is that if you took a cube, right, and we call this cube delta A, let's call this cube a small, again, sectional area of our material. We know that each surface of a cube, or this three-dimensional cube portion of our material, has a normal stress, which is perpendicular to it. And then it has shear stress, which is parallel to its surface, going in one of two directions. So let's take this surface right here at the top. You have the normal stress being sigma sub z, which is coming out of the top, out of the z face. And then you have tau sub yz, which is tau on this y-axis, going the direction of y on the surface of z. And then you have tau sub xz, which is on the surface of z, going in the x direction. And so forth and so on every single face. Now, one of the things we do in this class and at this level of mechanics of materials is that we simplify it a bit. And we begin to look at not just this general state of three-dimensional stress, we actually look at what we call plane stress, which is more two-dimensional. And so you look at this cube here at the bottom, we basically just look at a normal stress of sigma sub x coming out of the x face. We have the sigma sub y coming out of the y surface or y face. And then we have two shear components, tau sub xy. And then this side we'll also call tau sub xy, because these are actually equating to each other when the object is not turning, it's in equilibrium. So here's the thing I want you all to know, that this is one way that it is written. This is one way that you can conceptualize it in your head. But more commonly, what you will see in this class or in this particular chapter is it written like this, written as a two-dimensional plane, x and a y axis. Again, y has a normal force coming directly in line with the y axis on this face. And then you have a normal x force in line with the x axis. And you can think of this as the x face, and you can think of this as the y face. All right. So this is how we're going to be writing it. This is how you're going to be seeing it. But in addition to that, as I told you, to account for the fact that things and forces can be occurring at various angles, this thing could be turning, it could be in a different position at a given point in time, we're going to be using this two-dimensional plane stress image as a representation and turning it by angle, right? So here is basically the exact same illustration, but we have this angle theta right here, which represents the orientation of our stress component, right? Now, I want us to understand that it's going to involve conceptualizing the fact that for every angle, for every turn, for every position of this plane stress, there is a orientation, there's an angle, and then there's a value for which the maximum normal and shear stresses occur. That's basically what we're doing. We're looking at these particular orientations, these states of plane stress, and we're trying to determine what will be the maximum normal stress that this particular component or segment will experience. What is the maximum shear stress? And then also we'll get into a little of, well, what angle does that occur at? All right. So let's move on to our document camera. Again, we're in chapter 9, and chapter 9 is dealing with stress transformation. Right. And as I showed you before, we're primarily looking at it as a two-dimensional plane stress coming out in this direction, sigma sub y, coming out in this direction, sigma sub x. And if it's in equilibrium, that means that the same amount of this sigma sub y is going to be coming from this side. And the same amount of this sigma sub x is going to be coming out of that side. So you can think of those as just equivalents. And then we're going to draw our shear stress on this side and this side. They're going to cancel each other out, but this is designated by tau sub xy. And then likewise, to keep things in equilibrium, you got a shear stress coming here. The shear stress coming here. All right. But the angle. So in some cases, you will see, as I showed you before just a second ago, where you're going to have the orientation shifted just a little bit, and you're going to see that angle. However, you can also see it illustrated in this way. Well, right on that plane stress illustration, an angle will be drawn right here. We'll call that angle theta. Now, moving forward, one of the ways that this is analyzed when we see the angle, when we see our normal and our shear stress, is by drawing like a little triangle is what we've had. And what you will see, a triangle, which again illustrates the orientation of the stress plane. So this triangle will have an angle theta here, right? And we're going to treat this right here, right? This surface here, this hypotenuse surface, as the new plane, right? Or the new orientation for which the maximum normal and shear stress occurs. So we're going to be able to look at it like this. Here is a new y-axis. And we'll call that y prime. And then perpendicular to it, this is going to be viewed as the new x-axis. We're going to call that x prime, right? This is how we are analyzing a plane stress that has been designated, or we've been told orients a certain amount of degrees. So this orientation is going to represent how we're going to, again, find our maximum shear and normal stress. Now think about this, because this is a small sectional area, we can look at this surface right here, this hypotenuse surface, as delta A. All right, think about that. Think about this as a very, very small segment of a material. And so that this long hypotenuse surface is going to be called delta A. So if that is delta A, we have an angle right here. How will we determine what this surface is? What is this surface? Well, we know that this surface here, if it was talking about trigonometry, could be the hypotenuse times it's the adjacent surface. So this side would be delta A sine of theta. All right, that side is delta A. Based on trigonometry, this is delta A on the sine of theta. And so if you already thought ahead of where I'm going next and said that this side, in that case, is delta A cosine of theta, then you would be correct. Those are just the surfaces. Now, if this had a perpendicular force coming out of this side, which we see here, right? We already know that this is in line with the sigma sub y here, and this side had a, let's say a shear stress going in this direction. Shear stress tau xy. We would then rewrite our stresses in this case not purely as sigma sub y, but this particular stress would be now written as sigma sub y times the surface area of delta A sine of theta. And then this shear stress will now be written as tau sub xy delta A sine of theta. That's how we're going to now write our our stresses on each side, right? That's how we're going to write them now, because now we're looking at it as a new orientation. We're going to multiply the value times that surface area, delta A sine theta, delta A sine theta. All right. So likewise, if we were to do the same thing in this case, we were looking at, right, the shear stress, and we're looking at the normal stress on this side, what would it be in that case? Well, the normal stress obviously would be sigma sub x delta A cosine theta. And here, it will be tau sub xy delta A cosine theta. All right. But again, let's not get too confused. This is how we're going to notate it. But what we're ultimately trying to find is, what are these new maximum values that will give us sigma x prime, right? What will give us that? And tau, right? Because this here in this case is a shear stress. So we want to find this, and we want to find tau x prime y prime. Those are the things that we want to find. Those are the things we want to find. And so what I'm about to show you really quick is, this is one method. I'm about to show you the first method that we're taught on how to solve for these, and it is called the equilibrium method. Equilibrium method. Conceptually, you all already know this. Is when you sum the forces in the x direction, x prime direction now though, because x prime represents the new orientation. And when you sum the forces, and you guessed it, the y prime direction. So this is what we're about to do right now. I'm about to show you two examples of how we use the equilibrium method. Just to review again, of finding our sigma x prime and our tau x prime y prime based on an orientation angle that we now have, in which we can express using these trig functions. One more thing really quick to show you on here before I change the page is that we will have to write tau x prime y prime also times delta A times the surface. And then we will need to also write delta A here. And now you're going to see what I mean in just a second, right? You're going to see what I mean in just a second. All right, let's take a look at this one right here. This is problem 9-2. It says determine the stress components, right? And by stress components, we mean sigma x prime and tau x prime y prime. Acting on the inclined plane AB. So here's our plane A and B, right? So we're talking about this. It's going to be rotated. It's an inclined plane. And solve the problem using a method of equilibrium method, right? So first thing I'm going to do to make sure we're looking at things as clear as we can is draw this rectangle here in the way that we did on our last sheet of paper, right? So we have this angle here, 30 degrees. And we know that coming out of this hypotenuse side, we're now going to have a new x prime axis. And what we can do is draw out of this side is the y prime axis, right? So you got your y prime axis, x prime axis. What we already see here is that we have coming out of the top, what was coming out of the top is a 65 MPa. But might I remind you that because we are now at a rotation, this is going to be 65 MPa times delta A. And this is what, the sine or the cosine side? This is the cosine side of 30 degrees. Right? Now, what we also have are these shear the shear stress, right? And we know that on this side, there's a downward shear stress happening. And it is 20 MPa, correct? Because of what we learned, it's not just 20 MPa, it's 20 MPa delta A sine, because it's this side, of 30. What we're trying to solve for in terms of the stress components is this normal stress, sigma sub x prime, and the shear stress. It's normal stress and the shear stress, tau sub x prime, y prime. All right. Now, what we also need to remember is that this is going to be sigma sub x prime times delta A, because we're taking the stress times this little area. We're distributing across that area in the same way we distributed it across this area, writing the delta A cosine 30, and we distribute across this area, the delta A sine 30 on that side, right? All right, so let's do the equilibrium method. We're going to sum the forces in the x prime direction. That's what we're going to do right now. That's all we're going to do. So let's sum the forces in the x prime direction. We're considering this the positive direction here. We're going to keep it in line with how we drew it. So we have sigma sub x prime times delta A plus. Now, are all these stresses in line with the x direction? No, they're not. What we're going to need to do is make sure we are able to, we're going to make sure that we're able to align these forces with our new orientation. So what that would mean is we would need to look at this angle here. And know that that's 30 degrees. We would need to know that this angle here is also 30 degrees. And I realized I left off another force, another shear force, or I could draw it another way. Because just like we have the 20 MPa times delta A sine 30, we need to make sure we show that shear force here for that line there. And that one here, it would be 20 MPa, what, cosine, or delta A, sorry, delta A cosine 30. It's the same value here, but for cosine. Hope that's visible. Just for you all sake, I'm gonna write that again. Boom. 20 MPa delta A cosine 30. All right, so that's an angle here that's gonna be 30 degrees. That's an angle here that's gonna be 30 degrees. Also, there's an angle here. Angle here that's gonna be 30 degrees. So we're gonna have to take the x prime component of all of these forces. So let's start here with this one, right? So this is 30 degrees. We have 20 MPa, so 20 delta A cosine 30, right? That is the force, or that is the stress. That's the hypotenuse. But we're gonna have to multiply that by this arm, or this orientation, which is represented by the sine of 30. So we're gonna say sine of 30 on the outside of that. That's the x prime component of that shear stress. Got me? Next, what we're gonna need to do is say that this 65 is going up, and the x prime component of it is going that way, right? Because we see that in order for this side, for the resultant to be in that direction, this side is going that direction, and then this side is pushing it that direction. So that's going to actually be a negative. A negative, what is the hypotenuse of the resultant? 65 delta A cosine 30. But we just want the x prime component. So that's going to be times the cosine of 30. All right. Next, we got to get the x prime component of this one. So we're going to go ahead and write, because this is going down, so we know that this is this way and that way. So this is going to be plus 20 delta A sine of 30. Now I'll make it the x prime component. So times the cosine of 30. Are there any other values? We got this one here, x prime component of that one, x prime component of that one, x prime component of that one. So we can set this equal to 0. I'm going to set that equal to 0. Now, one of the things you can do is once you set it equal to 0 is that you can go through, and this is pretty much the case in every one. You can go ahead and cancel out all these delta A's, because you can just divide the whole thing by delta A. And then what you're going to want to do is then isolate sigma sub x prime to solve for it. 20 times cosine 30 times sine of 30 minus 65 times cosine 30 times cosine 30 plus 20 times sine of 30 times cosine of 30. Set that equal to 0 to solve for sigma sub x prime. And the value you should get when you do that is 31.4 MPa. 31.4 MPa. That gave us this value using the method of equilibrium. But we only did one. We only did one component. Next, we need to get this tau sub x prime, y prime, and we can do that exactly the same way. So let me see if I can just shift this up a little bit. Actually, I'll write it down here. I'll try to write it down here so you all can see it. Right there at the bottom. So if we're summing the forces in the y prime direction, sum the forces in the y prime direction, this is our positive direction. We're going to start things off this way by doing tau sub x prime, y prime times delta A. So tau x prime, y prime, delta A. Next, we're going to do a minus this one, because we got this force here is going that way and this way. So this hypotenuse is a combination of that direction and that direction. So this will be a negative. So a negative 20 delta A cosine 30, but that's going to be times the y prime component. So that is also cosine 30. Then we're going to come over here. This direction is a combination of this direction and that direction. So this will also be a minus 65 delta A cosine 30 sine 30. And then we're going to come over here and get this component, which is a combination of that direction and this direction. So that's going to be a plus. So plus 20 delta A sine 30. And then we need this component. So that's going to be, this face is going to be the cosine of 30. Am I correct there? Is this the cosine? This is cosine. I'm sorry, that's the sine of 30. The sine of 30. And that's it. We're going to set it equal to 0. We can count out all the delta A's, plug these in our calculator to solve for tau sub x prime y prime. And what you should have here is this number, tau sub x prime y prime equal to 38.1 MPa. That, my friends, is our other component, and it's the answer using the method of equilibrium. Right? Kind of involved, right? I understand, I get it. You got to make sure you get your trig functions right. But that is the method of equilibrium, and that is what we are instructing in today's lecture. I'm going to do another one, though. I'm going to do another one. The next one is right, pretty much the same level, but it's right after in the textbook. And so that is none other than 9-3. 9-3, we just did 9-2. It asks the same question. Determine the stress components, which is sigma sub x prime and tau sub x prime from y prime, on the inclined angle of the plane AB, and we're using this angle right here of 60 degrees. So let me go ahead and do what we did last time and write this triangle here as a way to illustrate this orientation of 60 degrees. We're always going to draw perpendicular to this hypotenuse. We're always going to draw that as our new x prime axis. Let's always do that. So this is the new x prime axis, or x prime. This is the new x prime axis. And then we can draw, and this one, it doesn't matter as much, but as long as it's parallel to this face, that should be our y prime axis, our y prime axis. Y prime, x prime, y prime. So that means that the shear stress here that we're trying to solve for is tau sub x prime, y prime. And let's go ahead and multiply that times delta A, because that's what we call this face. That's what we call this face. And then this side here is sigma sub x prime times delta A. And we look here, we only have normal stresses here. So we're only going to deal with the normal stresses. We have this 400 PSI, which means that it's going to be coming down on this side. That's going to be 400 times this face, right? So 400 times delta A, that's what that is, times the cosine of 60. And then we have this 650 PSI. It's going into the square, the plane stress. So we're going to draw it in this direction. And this is going to be 650 delta A times the sine of 60. That's how we're going to draw a triangle. And this is how we're going to do the method of equilibrium. Now, if we had some shear stress here, we obviously would need to draw shear stress like in our last one, but we only have normal stresses. So this is how we're going to draw our triangle in this case. Keep in mind again that this is delta A face. This here is delta A face, delta A times cosine. And then this side is delta A sine of 60, right? Let's not forget which surfaces are which. Now we're going to do the method of equilibrium like they tell us in the problem. We're going to solve that together. So the first thing we're going to do is sum the forces in the x prime direction. Sum the forces in the x prime direction. Let's start things off with sigma x prime delta A. Clearly determined in terms of our angle. We need to be able to determine what our angles are. And then this side right here, it's also 60 degrees. So it's going to be a negative 400 delta A cosine 60 times. All right, I just noticed a mistake. I drew this angle on the wrong side, right? Because the angle is going to rotate that way. So this 60 degrees angle should have been shown on that side. It should have been shown on this side, not this side. So this is 60 degrees. And this is our triangle. Hope that's clear to you all. Right. So what that means is we're going to do this 400 delta A cosine 60 here times the cosine of 60, because that's going to be this side that we're looking at, times the cosine of 60. And that's going to be negative because this value here is a combination of this direction and this direction. All right, so cosine of 60. Next, we're going to look at this value. This direction here is a combination of this direction and this direction. So that is a positive. It's going to be attributing to the positive direction of 650 delta A times sine of 60. Times, this is the direction, so that's going to be times the sine of 60, right? Hope everything is tracking for you, because this is trigonometry. I'm gonna go ahead and do this again. We're looking at this direction, sigma sub x prime times delta A. Then we're gonna look at what is this attributing in this positive direction. Well, when we look at the values, it's gonna be 400 delta A cosine 60, which is that. But we need the x prime component. The x prime component is this face, the cosine of 60. When you look at how the angle rotates out from that component. And that's going to be in the negative direction. Then we're going to look at this component of 650 times delta A sine 60. And are we going to do positive or negative? Well, when we look at how 60 degrees rotates out, we see that the x prime component is actually positive. So we're going to say plus, and it's this face. So it's the sine of 60. Set that equal to 0. Delta A's all get canceled out. We isolate sigma sub x prime, and sigma sub x prime is equal to negative 387.5 psi. All right, so that simply means that I wrote it in the opposite direction, and it means that yeah, that is our value. That is our value in that case. So I put a square around that. Now let's sum the forces in the y prime direction in order to solve for tau sub x prime y prime. So sum the forces in the y prime direction, right? In this case, this was the positive, and this is the positive in this case. All right. So now let's sum it up. We're going to have, this is equal to tau sub x prime y prime delta A. Next, let's look at what this is attributing. Well, if this is the angle coming out this direction and it's going down, that's actually going to be a negative, another negative 400 delta A cosine 60. And which component? Well, is this part of the triangle, which this is a 60 adjacent to the 60 degree angle. So that is going to be sine 60 degrees. Next, we're going to look at what type of component, the x prime component for this one. So we know we're going to start off with 650 delta A sine of 60. But we're looking at a negative direction, when we see how it swings out. So that's also going to be negative. And that face is the, it's the adjacent, it's right next to it. So that's going to be the cosine of 60. Set that equal to 0. Cancel all our delta A's, delta A. Do the math, the algebra. and the trig in your calculator, what you would get here is 455 PSI. That is the value of the shear component using the method of equilibrium, the method of equilibrium. Now that we went through that long method of equilibrium, I want to show you all another method, right? Another method that's going to be helpful moving forward. One that I can almost guarantee you'll like better than the method of equilibrium, though the method of equilibrium is a good way to make sure you're doing things correct. Pay attention to this next one. One is the method of equilibrium. This is what we just went over. But the number 2 method is just simply using the stress transformation equations. Stress transformation equations. So yes, in case you're wondering, there are equations that can simply get you to the point where you're finding your normal stress and your shear stress. Let me go ahead and write those out for you. And yes, you can definitely highlight these, put a box around them, take them to the bank. There's going to be a key for making sure you know what to plug into certain parts of it, particularly the angles. But let me go ahead and first write that out for you. So sigma sub y prime is basically, you're going to take the sigma sub x plus the sigma sub y, place that over 2. It's right here in your book in section 9.2. You're going to add that to the sigma sub x minus the sigma sub y over 2. Multiply that by the cosine of 2 theta plus tau xy sine 2 theta. That's your equation for sigma sub x prime. The equation for this here is negative on the sigma sub x minus sigma sub y over 2 times 2 sine 2 theta plus tau sub x sub y cosine 2 theta. These are the equations that constitute the second method for solving for these principal stresses, and they are called the stress transformation equations. So before I move forward, I want to make sure you understand where you're going to find these angles from, because if you're not careful, you're going to assume that whatever angle they show you in the image, oh, that's the angle you put in there. And it's tempting because this likely just kind of blew your mind after we went through all of that long process to say, oh, you tell me I can just plug it into equations? Yes, you can, but you need to make sure that you don't get tripped up right here on the angle. So you know how they gave it to you, and you're going to be seeing your problems like this 2-dimensional plane stress, right? And obviously you have your regular x subprime, then you got your tau xy here. This is saying that direction. And then you got here, you're going to have your tau sub x. I'm sorry, this is sigma sub y, and this is sigma sub x, right? And then you have, in some cases, you're going to be having like, I don't know, like an angle here. We just saw these, right? Well, what's going to happen is, as you draw your, let me do this another way. Let me show the angle right here. Right? Scratch this angle. So the angle right there, right? So as you draw your rectangle, or your triangle, I'm sorry, your triangle, and basically you're going to come up with this new orientation of x prime, right? And your new orientation of y prime. Though you may have an angle here, right? Don't get caught up in using the angle that they show you. I want you to look at what is the new angle of the new x prime with respect to the original x axis location. So the original x is in this direction, horizontal, right? But in this case, when you have your new rectangle, your x prime is going to be a certain number of degrees away from your original x-axis. And in some cases, whereas say for instance, this is 30 degrees, it will be the same angle. But in other cases, it won't be. It won't necessarily be the same angle. And I'm gonna see if I can find an example for you really quick. I want to make sure you all don't get too confused about which angle to use in this equation. Okay, I'm just gonna write one up real quick. Let me draw one up really quick. Right? Some cases they're going to show you, you're going to get in this class some problems where you have an already rotated plane stress state. And then they're also going to say, well, there's an angle here that we're showing you of, say, 30 degrees here. But before you draw your rectangle, just know that, you have these stress values. It's going into the block of 80 MPa, right? And then you have another one, this shear stress here, which is counteracted by that shear stress there. This one is 30 MPa. All right, you all tracking? All right, cool. And then you have, obviously that's going to be another 80 MPa right there. But then you have this tension force in the y-axis of 40 MPa. Got another 40 MPa right there. Yep. And so they'll say, all right, cool, that's fine. Let's solve the problems. Let's use our equations. Let's use the stress transformation equations to solve for our stress components. Right? Boom. Simple enough. Well, let's look at how this triangle would look. This triangle would look something like this if we were to take that triangle and just draw it. There's our 30 degrees. And remember now our x orientation is perpendicular to that face there. So this is x prime, right? This is x prime. And then we're going to say that, say maybe this is our y prime. Our y prime direction is perpendicular. Now, what we want to remember is the angle that we're going to use for our equations is the distance that this has now rotated from the original direction of the y or the x axis. So the original x axis is coming out of this side like this. So we want to know the angle from here to here. Well, based on this angle here, we already know that this right here to here is 30 degrees. This is 30, right? We can look at that and see that. And then since this is perpendicular to this axis, we know that this is 90. So the question is, what is the total angle of this new x prime orientation compared to original x orientation? That is correct. It is 120 degrees. All right, don't miss that. Don't miss that. So now when we get into our bag and start plugging in these equations, let me just do this sigma x prime right here in front of you. This one would be sigma x prime is equal to, what is sigma sub x? Well, that's 80, right? But is it a positive 80 or negative 80? It's a compressive force. It's going towards the block. So this is going to be a negative 80 plus sigma sub y, which is 40. Boom. We put that over 2, because that's what the equation says. Plus, we also have, in this case, a negative 80 minus, because that's what the equation says, sigma sub y, which is 40. That's going to be over 2. Cosine 2 times the angle of 120. That is correct. Which I could have went ahead and multiplied and made 240, but we'll keep it right there for now. Plus, now when we look at this tau sub xy, we want to look at this right side, right? If this right side is going down, then this is a negative number. If this right side is going up, we'll use it as a positive number. But it's going down in this case, right? It's going in the negative direction of the y-axis. So we're going to say that this here is a negative 30 times the sine of 2 times 120. All right, let me go ahead and write the next one before I put in my calculator. Let me write the next one though. Tau sub x prime y prime. This equation looks like this. Starts off with a negative on the outside. Same thing, negative 80. And then we have a minus 40 over 2 times sine of 2 times 120 plus tau sub xy, which is 30. It's not just any 30, it's a negative 30. Cosine 2 times 120. So now we can solve for both of those. Sorry about that. Let's solve for both of those. Let's plug this in the calculator. I encourage you to join me with that to make sure we're on the same page. So negative 80 plus 40 plus 40 2 plus negative 80 minus 40 2 cosine 240 plus 30. And the answer I have for the sigma sub x prime is 35.98 MPa. All right, do this next one with me. Hope you all concur so far. All right, boom, we got boom. Sine 240. Yep, and the answer I got here is a negative 36.96 MPa. There we are. So those are our values. Hope this all helped you out really quick. Again, this is a whole lot simpler than the method of equilibrium, but just make sure you're plugging in the right angle, as I showed you, and the right signs as it relates to these values that you're giving in your plane stress state. All right, hope that helps. All the best on your upcoming assignments, and I will see you all in the next lecture. Take care. Peace.